Okay. So first things first, last time we started kind of finishing up the section on taking derivatives of parametric curves, right? And there was a couple of formulas at the very end, one of which we ended with last time, that had to do with arc length of a curve, okay? So if I want the arc length of a curve, so let's just say, so arc length, so suppose I have x equal to some function of t, and I have y equal to some other function of t, okay? And that the curve is traversed between A and B, then the arc length of the entire curve, which by the way, oftentimes is notated by s, okay, lowercase s, is going to be given by the integral from A to B. Okay, so you let the parameter run its course, integral from A to B, the square root of dx dt squared plus dy dt squared. Okay, it's a square root of that junk, dt. Okay, now that can make for some pretty gnarly integrals because you have that unfortunate square root sitting there. Okay, and by the way, the proof of this isn't all that difficult. It has to do once again with the Pythagorean theorem. Basically, what you do is you think of dx as a tiny distance in x and dy as a tiny distance in y. And so you're going to get something like this, okay? So you kind of get a tiny distance in x and a tiny distance in y. And what's the length of the hypotenuse of that thing then? It would be the square root of what? Dx squared plus dy squared. And basically what you do is you kind of reimagine that in integral form. And you end up getting the formula for arc length, okay? And the example that we were working on last time, if you'll recall, had to do with, okay, and by the way, so here's kind of a picture of what's happening. You know, I have some kind of curve that might be doing all kinds of nonsense, okay? So this is the starting point, t equal to a, and I'm kind of moving along this curve in this direction, and this is the ending point at t equal to b. And this thing will compute the arc length of that entire thing. But we ended on an example last time. It looked like it was going to be difficult. It was, x equal to r times theta minus sine theta, and y was equal to r times 1 minus cosine theta for 0 equal to or less than theta equal to or less than 2 pi. What was this? Just to make sure we were all on the same page, what was this thing? What curve is this going to give us? This is the cycloid, and it's one arc of the cycloid, yes? Okay, so this is one arc of the cycloid. Okay, one arc of the cycloid. So, I mean, if I were to draw a picture of this, it looks something like this. So, like this, okay? So this is, I'm right here at t equal to, or not t, what am I using in this case? I decided to use theta for some reason. Theta equal to 0, and then I'm here at theta equal to 2 pi. And we let Desmos to kind of do some magic last time to try to tell us like what the answer should be. Okay, but I want to go through that rigorously. And last time we computed like dx d theta and dy d theta. So let's go ahead and recompute those. Dx d theta, what was dx d theta? Okay, r was like a constant. Dx d theta is going to be that constant coming along for the ride, r. And then what's inside of the parentheses for dx d theta? What's the derivative of theta? 1. Minus, and what's the derivative of sine theta? Yeah, cosine of theta. And then what is dy d theta? dy d theta equals, well, the derivative of 1 is just, the derivative of 1 is just 0, okay? So, but what's the derivative of cosine? You guys realize this is kind of weird, right? Dx d theta is actually equal to what y is in this parametrization, which is sort of weird, but okay, that's just an interesting byproduct of this thing. What's dy d theta? What did we come up with? Yeah, it's just r sine of theta. Because the derivative of 1 is 0 and the derivative of minus cosine is positive sine, okay? So we have those. So we can invoke the arc length formula, okay, to try to compute this thing. And I'll write that on the next slide here, okay? So the arc length, S, is going to be equal to the integral from 0 to 2 pi, the square root of some nasty stuff here, right? It's going to be r times, right, dx d theta squared, r times 1 minus cosine of theta, all of this squared, yes, plus dy d theta squared. Well, dy d theta was, you know, r sine of theta. That squared d theta, yeah? And look, I can factor out the r squared, can't I? I'm going to have an r squared from each one of these summands. I can factor that out, right? And take the square root. And I will get r times the integral from 0 to 2 pi, square root of 1 minus cosine of theta squared plus, let's see, what am I going to have left here? Sine squared of theta d theta. See what I did there? I factored out r squared from each one of those summands and went ahead and took the square root. That's just a constant that I can pull out. Yeah? Now let's just expand this out. You get r integral from 0 to 2 pi, square root. Okay, this is going to be 1 minus 2 cosine of theta plus cosine squared of theta. I just expanded out that 1 minus cosine theta quantity squared plus sine squared of theta d theta. But what's cosine squared plus sine squared? That's just 1, right? That's 1. Therefore, what do I get here? R integral from 0 to 2 pi. Okay, I have a 1 sitting here, and I have a 1 arising from the cos squared plus sine squared. So overall, it's going to be the square root of what? 2 minus 2 cosine theta d theta. Okay. Now, I could factor out 2, can't I? And pull out a square root of 2 in front of everything. See what I mean? Okay. And if I do that, I'm going to get, square root of 2r, okay, integral from 0 to 2 pi, square root of 1 minus cosine of theta d theta, okay? And so we've got this thing down to something that looks relatively simple compared to what we started with, yes? We factored out 2, that was under the square root, now we have the square root of 2 times r out front of this thing. Now, this is one of those like tricky integrals that we would have encountered in, what was it, like the first section of chapter 8, remember that? Okay, one way that we can deal with this is the following. Let me kind of erase the d theta here, watch. I could actually multiply this thing by the square root of 1 plus cosine of theta over the square root of 1 plus cosine of theta. And you might say to yourself, what? What is that? Well, what that's going to do is really kind of fix up the upstairs a little bit for us. Because what's going to happen if I multiply that square root of 1 minus cos theta times the square root of 1 plus cosine theta? Basically, it's going to be the square root of the product of those two. But what's 1 plus cosine times 1 minus cosine? What's that going to be? 1 minus cosine squared, right? So it's going to be the square root of 2 times r, the integral from 0 to 2 pi, okay? It's going to be the square root of 1 minus cosine squared theta over the square root of 1 plus cosine of theta. And you might be saying to yourself, oh my goodness, that's like way worse than what we just had a couple of seconds ago. But I promise it's not, okay? I promise you it's not, because what's 1 minus cosine? Yes. What do you mean here? Would those? No, because they're not the same thing, right? It would be if it was like the square root of x times the square root of x, then it would just be x, yes? But here it's the square root of one thing and the square root of a different thing. So you have to just do the multiplication under the square root. Does that make sense? Okay. So what is, let me just ask you, okay, square root of 2r integral from 0 to 2 pi, okay? It's the square root of 1 minus cosine squared. What is 1 minus cosine squared? That's sine squared. And this is where I have to be very, 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 very careful. And this is where Desmos, which by the way is a stupid machine that some human programmed. Does that make sense? Desmos doesn't understand that it even exists. Yeah? Or not Desmos, Wolfram Alpha. It doesn't matter, right? Either one of those. They're both stupid machines. Wolfram Alpha is a machine that does not even know it exists. It doesn't know anything, yeah? So you have to understand, yesterday we were getting conflicting answers. Do you remember that? It was like, we said, okay, it looks like the answer should be 8r, but in the case of r equal to 1/2, it doesn't look like that formula works. Well, that's because Wolfram Alpha is a stupid machine, okay? And we're about to see why that happens to be the case. Okay, so watch this. This is the square root of sine squared of theta, right? The square root of sine squared of theta divided by the square root of 1 plus cosine of theta d theta. And this is where our humanity is brought to bear, okay? Because you might be tempted to say that the square root of something squared is what? That's something. But what if that something is negative? Do you know what I mean? If that something is negative, then you need to take the absolute value. Does that make sense? The square root, by the square root, we mean the positive square root, yeah? So the square root of t squared is the absolute value of t. And now you might say to yourself, why is that relevant here? Well, because here I have the square root of sine squared. And what's the problem with sine? It could be negative. In fact, it is negative on this interval. Do you know what I mean? It actually is negative on this interval. Now, here's the thing. Well, okay, yeah. So let's just kind of think about this together. Let's go over to the next slide here because I'm running out of room. So I'll just write down what it was. It was the square root of 2r, square root of 2 times r, integral from 0 to 2 pi, square root of sine squared of theta over the square root of 1 plus cosine of theta d theta. Now, where is, right, this is supposed to be sine squared, not sine of 2 theta. This is sine squared. Now, where is the sine function? Where is the sine function positive? Between 0 and pi, okay? And cosine runs through a gauntlet of values between 0 and pi. Does that make sense? So I'm thinking about the denominator. Sine is positive between 0 and pi, yes? And cosine runs through its gauntlet of values. It starts out at 1, and then it goes down to -1 by the time you get to pi, yes? But then once I go from pi to 2 pi, isn't cosine just going to run right through its gauntlet of values again? You know what I'm saying? And similarly, so is the sine function, except they're going to all be negative, yeah? So look, isn't this quantity just going to repeat the same values that it did from 0 to pi? between pi and 2 pi, yes? It's going to run through the exact same values between 0 and pi, and then from pi to 2 pi. So what's one thing I could do to kind of capture that? Do I really have to integrate from 0 to 2 pi? I can go from 0 to pi, but then I would have to do what to the value of the integral? Double it. Double it. Do you know what I'm saying? I have to double the value of the integral. So this is 2 square root of 2 r, the integral from 0 to where? Pi. And the nice thing about being between 0 and pi is sine is positive, yes? Therefore, the square root of sine squared is just sine. I don't have to horse around with absolute values anymore, yeah? Okay, so this is just sine of theta. And this is where not Desmos, but they're both stupid, okay? They're just helpful, but they're both not, I mean, look, the reason I say this so much is people talk about machines nowadays as if they know anything, yeah? All they do is it's a collection of human initiated information, yes? So you have to be careful about that, okay? So sine theta over the square root of 1 plus cosine of theta d theta. Now, let me ask you a question. Why is that any better? Is there a substitute? Yes.
What happened to the absolute value? Like, so you said like square root of t squared is plus or minus t.
No, it's absolute value of t.
Yeah, so absolute value of t. So why isn't sine absolute?
Because I'm between 0 and pi. And what's true about the sine function between 0 and pi? Therefore, the absolute value makes no difference. That was the whole point of us trying to kind of restrict between 0 and pi and making the observation that between pi and 2 pi, like the absolute value of sine is just going to make it have the exact same values. That's why we doubled the value of the integral, yeah? Okay, so what's a substitution I can make here? What do you guys think? U equal to, well, why not just 1 plus cosine of theta? Why not just go for the whole show here? You know what I'm saying? Then what is du? Negative sine of theta d theta, which is almost what we have here. So in other words, negative du is equal to sine theta d theta. Okay, so let's kind of rewrite this thing now. So this is going to be equal to, let me put a minus sign out here. Okay, minus, right, because it's minus du, minus 2 square root of 2 r. The integral, I'm not gonna touch the limits of integration because I might change those. And it was minus sine theta d theta, or sorry, minus du is equal to sine theta d theta, right? So it's just du, right? I just have to make sure I have to take into account du. And then what's the rest of it? It's 1 over the square root of what? Of u, which is basically u to the minus 1/2. And if you want, you can actually change the limits of integration. When theta is 0, what is u? When theta is 0, what is u? 2. Okay? And when theta is pi, what is u? When theta is pi, cosine of pi is -1, correct? So what's u if theta is pi? 0. This makes it so I don't have to go back and resubstitute. Does that make sense? I've just changed this thing into an integral in u instead. And by the way, these limits look backwards, but what do I have sitting out front here? A negative, which really helps me out here. So let's actually write this down. So this is going to be 2 square root of 2 r integral, incorporate the minus sign to make this from 0 to 2, u to the minus 1/2 du. Okay, questions so far? So we're about to kind of finish this thing off here, but any questions so far? Yeah, that's right. I just, I plugged in theta equal to 0, and I plugged in theta equal to 2 pi, and then the these guys correspond to each other and these guys correspond to each other. Does that make sense? Yeah. Okay. All right, other questions? All right, well, what's the antiderivative of u to the minus 1/2? 2u to the 1/2. Yes? 2u to the 1/2. Exactly. This is going to be 2 square root of 2 r, and it's going to be 2u to the 1/2, which is the square root of u, evaluated between 0 and 2. Yeah? And if I plug those things in, of course, if I plug in u equal to 0, I don't get anything. But if I plug in u equal to 2, I get 2 square root of 2. So this is going to be 2 square root of 2 times r times 2 square root of 2. So what do we get? 2 times 2 is 4 times the square root of 2 times the square root of 2 is another factor of 2, which gives me 8 times the radius. Wasn't that one of the options that Wolfram Alpha spit out? Yeah. But that tells us that when the radius was 1/2, it gave us the wrong answer. What did it give us when the radius was 1/2? 2. Wrong. What they did is they incorrectly, I'm positive because I went through and kind of checked this, they incorrectly sort of let some stuff cancel on one of the intervals, yes? And that was inappropriate, okay? But this is interesting. So one arc of the cycloid is always 8 times whatever the radius of the wheel is. That's kind of interesting, right? You would think there would at least be like a pi or something in there. But 8? Where does 8 come from, right? That's just sort of bizarre. So one arc of the cycloid is going to be 8 times whatever the radius of the wheel is, which is precisely 8 times the radius. That's fairly amazing. We should all be shocked and awed by that for sure, okay? All right, any questions on that? Questions? All right, well, I think that's pretty cool. So let's go in here. So that was this guy right here. Okay, so let me just say, what we ended up getting here was that the arc length of, right, so let me just write this in here. Arc length of one arc of the cycloid. We used the formula to show that this was, and now it's annotating this thing, disable and hide names of annotators, okay? This ends up being 8 times the radius, which is amazing, okay? We did a little bit of interesting calculation to pull that off for sure, okay? I wanted to move on to surface area for a surface of revolution, okay? Surface of revolution. I always laugh when I think about that because it makes me think about like revolting surfaces or something. Does that make sense? It's like they've risen up, you know, it's like they've risen up in revolt, yeah? So it's a surface of revolution, okay? So here is the formula that's given to us. And by the way, you did something like this at one point where you kind of were rotating a curve around like the X or the Y axis, yes? And you had to compute the volume and the surface area of that thing. The volume, you use like the disc washer method or the disc or the washer method, remember that? Or the shell method, those ringing a bell, okay? And you also had the formula for the surface of revolution as well, okay? Now, here's the formula. Doesn't this look familiar? This guy right here, square root of that stuff. What does that remind you of? What does that remind you of? How about let's look at the previous slide. Does it remind you of that? Yeah? It's the same factor. So you have like, this is like the arc length factor. The arc length factor. And this 2 pi times g of x or g of t, what does that remind you of? 2 pi times something. What does that remind you of? Circumference of a circle. Yeah? So this is the circumference factor. Okay, what's going on here is basically to compute the surface area, what you're doing is you're getting a bunch of tiny little belts like this. Oh man, you got to admit that's a pretty impressive picture right there. So that was a clutch drawing. I wasn't expecting that one to go that well, but well, let's see. So actually, what you have here is you have a tiny amount of arc length, and then you have sort of a distance around. But in order to get that distance around, I don't want to mess this thing up, right? I'm really excited about this picture right now. Okay, you have sort of like you have a radius. Okay, and what is that radius? Well, you know, if it's y, so in this case we have y sort of acting as the radius. This is like y equal to g of t. Okay, so what is 2 pi times that? It's the distance around this thing. Do you know what I'm saying? Okay, so the circumference of this thing, right? The circumference of that thing is equal to 2 pi times g of t. And what you do is you take a tiny piece of arc length and you multiply that thing all the way around, because after all, if I were to slice that and unravel it, wouldn't that just be a rectangle? Do you see what I'm saying? If I were to slice this thing and unravel it, okay, so if I suppose I take this thing and I actually slice it like right here or something, right? So there's a cut. Then what's this thing going to turn into? Well, it's going to be a rectangle, okay? That wasn't as clutch, okay? What I just drew was definitely not as clutch, okay? The arc length right here, that's still the arc length right there. And where's C in this picture? Well, C is right here. Does that make sense? So if I wanted to compute the area of that thing, what would I do? I would go C times the arc length. Does that make sense? Right, so the area of this is equal to C times the arc length. That little piece of arc length right there. And that's exactly what's sitting right here. Do you see that? It's like the circumference at a given point times a little piece of arc length. And then when I integrate, it's just going to add together all of those areas. It's like the areas of these belts. These are basically like belts all the way around. Does that make sense? Yeah, like the area of these belts going all the way around the surface, the revolved surface. Okay, so that's kind of a makeshift explanation of this the area of the surface of revolution. Okay. All right. So how does this thing play out in practice? So again, the reason I showed you that, it's easier to remember. You have like the 2 pi g of t, that's like the circumference piece. And then you have this junk right here, which is the arc length piece. Okay. How does this play out in practice? Well, let's look at one example here. Okay. So find the area of the surface resulting from revolving the curve given by that, where theta goes between 0 and pi over 2. Now, this is a test of your mettle, or just of remembering some of the things that we've parametrized in the past. What is this going to give us? X equal to 4 cos theta and y equal to 4 sine theta. Do you guys remember? What kind of a curve is that going to be? A circle. Of what radius? 4. But I only let theta go between 0 and pi over 2. And by the way, it's going to be centered at the origin. Yes? But I only got to let theta go between 0 and pi over 2. So what am I dealing with here? I'm dealing with a quarter of it. Yeah, so it's like a quarter circle. And the radius of this thing is 4. Okay, and you're going to be moving in this direction along that curve. But what am I being asked to do with this thing? Revolve this curve about the y-axis. Okay, revolve that thing about the y-axis. Okay, so that means go like this. What is that going to generate? What kind of a shape is that going to be? A half sphere. Yes, a half sphere. Okay, so if I do that, let's see. This. Okay, let's see if I can pull this thing off here. There's that. Okay, that's looking pretty good. Okay, but we would probably want to try to slice this thing like this. Watch. Okay. See what I'm saying? You probably want to slice this thing like this, which probably means that I want to use, like if this is the point x comma y right here, then what is the radius of those circles? And incidentally, like I'm going to let I'm going to let those circles kind of go up and down on this thing. Does that make sense? I'm going to let those things kind of go up and down on that sphere. So what is the radius given by, though? Is it given by x or is it given by y in this case? It's given by x. Yeah? So the radius is given by x, okay? So the radius here is given by x, this guy right here, okay? As we kind of travel along this thing, right? T is going to move us along this thing, yes? The radius of those little belts is given by x every single time. So the surface area is going to be 2 pi, the integral from where to where? 0 to pi over 2. And then it's going to be 2 pi times the radius, yes? And the radius here, is it x or is it y? X. Okay, so it's going to be 4 cosine of theta times the square root of, okay, I need like dx d theta, but that's easy. That's just -4 sine of theta. And what's dy d theta? 4 cosine of theta. So I have to square both those things and add them together. So that's going to be 4 squared sine squared theta. That's dx d theta squared plus 4 squared cosine squared theta d theta. Now, do you see a simplification I can make here? Is there a particular simplification I can make in this case? Yeah, pull out the 4 squared, take the square root, that's just 4. But what's sine squared plus cosine squared once I do that? 1. So actually just 4 comes out, right? So this whole thing right here is just a really complicated way of writing 4, excuse me, yes? Okay, then I have a 2 here, I have a 4 here, and I have this 4, yeah? So what am I going to have overall? How many pi? 32 pi. Okay, and it's going to be the integral from 0 to pi over 2. And what's left? What is the only thing left? Cosine of theta, d theta. So finally, it's going to be 32 pi. What is the antiderivative of cosine? Sine. Sine theta evaluated between 0 and pi over 2. Well, sine of 0 is 0. What's the sine of pi over 2? 1. Right, so what's the answer? 32 pi. Okay, and look, we should have a way of checking this thing. This after all, when you think about it for a minute, right, this was basically a sphere of radius 4 we were dealing with, yes? A sphere of radius 4. So we get a surface area of 32 pi. Do you guys remember the formula for the surface area of a sphere? No, that would have been the volume. Volume is 4/3 pi r cubed, yeah? Do you remember what it is for surface area? It's 4 pi r squared. That's for the entire sphere, yes? So that's for an entire sphere, yeah? Surface area of an entire sphere is given by that. So what should this surface area have been? Let's kind of just check this. This surface area, you know, just to check our answer, it should have been half. It's half a sphere, yes? Half 4 pi. Okay, what is the radius in this case? What's the radius? 4 squared. Does this work? Yeah, because 1/2 times 4 is 2 times 16 is 32 pi. Check. Yeah. So in that case, we actually had the ability to check the answer, but the formula gave it to us anyways. Yes, Jared. Yeah. Does that make sense? Okay. So we have arc length, we have surface area. We know how to take derivatives. We know how to take higher order derivatives. These are exciting times. Okay, for sure. Any questions on that before we move on? We're also getting to stretch our legs a little bit with some integration stuff, but okay. Okay, that's that. We are done with that. And we are going to move on to the next topic at hand. Okay, which is polar coordinates and graphs. Polar coordinates and graphs. Now, what polar coordinates is all about is really just another way of, it's another way of thinking about representing points in the plane, okay? So far, representing points in the plane, you have like an X and you have a Y, correct? And essentially, that's called a rectangular coordinate system, and we'll kind of see why that happens to be the case. It's also called Cartesian coordinates after the philosopher Rene Descartes, okay? But what we're going to do now is actually represent points in the plane using circles. That's going to involve some clever thinking on our part, using some of our newfound parametric skills, okay? All right, so in a rectangular coordinate system, okay, in a rectangular coordinate system, you just locate a point by its horizontal and vertical distance. And you guys understand why we would call it rectangular system, right? Because if you think about it with respect to like the X and the Y axes, what kinds of things do you get? You get rectangles, correct? That's one reason why you call it a rectangular coordinate system, okay? And you talk about it in terms of its horizontal distance from the origin and its vertical distance from the origin, but its directed distance. Remember we talked about directed distance before? Where did that come up? What was directed distance? What was that all about? Do you remember what the context was? Yeah, it was parabolas, yeah? Directed distance, so for instance, if X was negative, you would move to the left. If X is positive, you would move to the right from the origin, our anchor point, the origin, okay? If Y was positive, you move up. If Y is negative, you move down, okay? So that's how the rectangular coordinate system works. And you get rectangles, if you think about it. That's sort of the geometric object at hand. But what we're going to do is kind of change the game. In a polar coordinate system, we fix a point called the pole and a ray called the polar axis. A ray sort of emanating from that pole. Okay, and just out of convenience, we oftentimes will just imagine the pole being simply the origin, the same thing that we were using in the case of the rectangular coordinate system. Okay, you have rays emanating from this pole at various angles. Okay, so these rays, they emanate, that's kind of a fun word. It means come out of, yes? Emanate from the pole at various angles with the positive x-axis. Okay? So that's kind of the basis of what we're going to be doing here in this polar coordinate system. Okay? So let me get rid of this. So here's what's happening here. Here's our pole. Okay? Okay, and you have this polar axis. Then you have rays that kind of emanate from that, and then you kind of record the angle between that polar axis and this thing. Now, out of convenience, like I said, we oftentimes just put that pole right at the origin, and the polar axis, I was hinting at this in what I just wrote, but the polar axis, you basically identify with which axis, do you think? So the pole, you identify with the origin. What do you think you identify the polar axis with? Well, the x-axis, okay? And then these are the rays that kind of emanate from the origin at various angles, okay? So how do I identify this point right here? Well, I identify it by the angle that's made with the polar axis and the distance from the pole. And you kind of notate this thing by r comma theta, where r is the distance from the pole and theta is the angle made from the ray going through this point and the polar axis. Yeah? So that's how this is going to work. Any questions on that? We'll sort of look at some examples here, but I just want to make sure the setup at least is clear. Okay. To plot a point r theta, you go r units along the polar axis and then rotate. Right, you can kind of think about, this is why circles are important. Okay, so you can kind of think of this as at distance r, and you kind of rotate by an angle of theta all the way up to that thing. You go r units along the polar axis and then rotate by theta degrees, yeah, or theta radians, however you're thinking about things. Okay? All right. So here's how this thing is going to work. Here's our pole in the middle right here. Here's our polar axis right here. Okay. Polar graph paper is marked in unlabeled circles centered at the pole and at angles which are set distances from the polar axis. Okay. So these circles are at set distances away from the polar, or at set distances away from the pole, right? And you have all the things that are at distance 1 or 2 or 3, etc., away from that pole. And you also label these various angles from the polar axis. Okay. So we'll actually label some points here next. Okay, plot the following points in polar coordinates. Okay, 5, comma, pi over 3. Okay. That means how far away from the pole are we? 5. And what's the angle made with the polar axis? Pi over 3. Okay. So here's how that looks. Okay, so here's the pole. 1, 2, 3, 4, 5. This is 5 units right here. And then you rotate this thing by pi over 3 radians, yes? And so you end up right here. Okay, on this ray right here. Okay? Does that make sense? Okay, so that's 5 comma pi over 3. Okay? Next, what about -5 comma pi over 3? What? I thought we said that it was always distance from the pole. Well, it turns out for convenience, it's nice to be able to allow negative radii. And what that means is you basically, let me kind of draw this. If I think about this line that contains that point, instead of going out a distance of 5 in the positive direction of pi over 3, you actually are going to go backwards. Okay, 1, 2, 3, 4, 5 units and end up like right there. Okay, so it's kind of convenient to actually be able to allow us to go forwards and backwards, depending on whether the radius is positive or negative. Okay, all right, so Let me clear that. So we place this point on the same radial line, but go in the opposite direction as for r equal to 5. So that's why there's that orange point right there. Does that make sense? So you basically, you can almost think of this as like a rotated x-axis or something, yes? Where you have the origin at the pole and you go out 5 units if the radius was 5, but if it was -5, I would go backwards 5 units along that same line. Does that make sense? Go backwards 5 units along that same line, okay? What about 0 pi? Somebody tell me where that's going to be. Where is 0 pi? The origin. Yeah. Does it even matter what the angle is? No. I could have given any angle and I would have been at the origin. Yeah. What about 2 comma minus pi over 6? Why don't you just for a minute kind of think about that. Okay. Think about where 2 comma minus pi over 6 would actually be located. Okay. Okay. All right. So you guys realize, like if this is my polar axis right here, then pi over 6 is this angle, yes? But here I'm saying to go which direction? Negative pi over 6, so you're going down here, yeah? Okay, and then it says to go out 2 units, so you're going to go along this radial line, yes? Go out 2 units, so where's that going to be? 1, it's going to be right there or something like that, yeah? Basically, 2 units out along that. I don't know if you can really see that. Let me use red. Like right there. Yeah? All right. Oh, the thing got shifted in going from one slide to the next, but yes, that is where it would be. Yes, right there. I marked that thing in blue. Okay. What about -2 negative pi over 6? What do you think about that? -2 negative pi over 6. Okay, let's think about this radial line right here. -2, -2, negative pi over 6. Where's that going to be? Just in the opposite direction of where that blue point is, yes? So 2 units kind of backwards along that thing, okay? So it's going to be right there. See that purple point that just emerged right there, yes? So that's -2 comma negative pi over 6, okay? Next. What about 5, 7 pi over 3? Think about that for a second. 5 comma 7 pi over 3. What do you guys think about that? By the way, you notice these points are color-coded to the things, right? It's like red, orange. See what's happening here? Just want to make sure we're clear about that. Okay. What about 5 comma 7 pi over 3? What do you guys think? What's that? Oh, yeah, the same as number 1. Yes, it's the exact same as number 1 because basically we've just gone around the circle, like because what's 2 pi? 2 pi is 6 pi over 3, yes? You add 6 pi over 3 to pi over 3, you get 7 pi over 3. So really all we did is we went around the circle one more time. We're going to be right back on the red point. Since 7 pi over 3 is coterminal with pi over 3, this is just another name for the first point we plotted. And indeed, polar points have many names, yes? Because you can just keep going around those circles. Do you see what I'm saying? And you have the flexibility of positive and negative radii, yeah? Positive and negative radii also give you the ability to kind of rename points, okay? Yes? The unit circle? This is a whole bunch of circles, yes? Yeah, so I mean, the angles just kind of go out forever. Does that make sense? Along those rays. That's what I meant by ray emanating from the pole. Yeah? Okay. Yes.
Is it possible to make this graph 3D?
Yes, there is something called, there is something called cylindrical coordinates, which basically is a three-dimensional version of these. There's another thing called spherical coordinates, which is also a three-dimensional version of these, but they kind of emphasize different things. Okay, good question. All right, other questions? Spherical coordinates, you measure the distance from the origin in three-dimensional space, and then you have to give a couple of angles to kind of distinguish what point you're talking about. Cylindrical coordinates, you basically use r and theta, just like we do here, but then you just give a z coordinate also. Okay? So cylindrical and spherical coordinates are a three-dimensional version of these. Yes. Okay? Other questions? Okay. Let's talk about converting between polar and rectangular forms. We need to find relationships between the two, yes? Okay. And like I said, the way we do it is by putting the pole where? Where do we put the pole? At the origin. And where do we put the polar axis? On the x-axis. Yes? Now, then, the radius is the hypotenuse of this little right triangle. See what I'm saying? Yeah? So for instance, you know that sine of theta is equal to, right? Sine of theta is like opposite over hypotenuse, yes? So sine of theta would be y over r, and cosine of theta would be x over r. And therefore, what's x in terms of r and theta? Well, it's r cosine of theta. You see what I'm saying? And y is r sine of theta, yes? So x is given by r cosine of theta, y is given by r sine of theta. This ought to remind you of parametrizing a circle of radius r, doesn't it? Right? It should remind you of that. Remember, we just did an example in the surface area formula where we had r equal to 4, in fact, okay? So the relationship between r and theta and x and y is given by that right there. And by the way, what's tangent of theta equal to? What's tangent of theta equal to? Y over x. There's also some other things. For instance, we have the Pythagorean identity. Like x squared plus y squared is always what? R squared, that's right. You have to be careful about taking square roots though, because R could be negative, yes? You have to be careful about that, but certainly this Pythagorean identity always holds, but be careful about taking square roots, okay? All of these little identities, which kind of fall out of that right triangle relationship, are the bread and butter of converting between rectangular and polar coordinates, okay? And kind of go back and forth between the two. Right? To convert from rectangular to polar form, look, if you give me an x and a y, I can figure out what r is by using r squared equal to x squared plus y squared. I can figure out what theta is by using tan theta is equal to y over x. And you could use arctangent, yes? Like theta, you could say that theta is equal to arctan of y over x. Right, the inverse tangent function. Or you can just think about, okay, y over x is this, therefore what's tan theta is equal to that, what must theta be? Okay, so that's how you go back and forth between polar and rectangular form. Okay, these two things going on right here. Does that make sense? We're just doing some trigonometry here, but just want to make sure it makes sense. And using the Pythagorean theorem. Okay. All right, we'll finish with this example, right? The rectangular point 1, -3. So this is x and this is y. Write this in polar form. Well, what's r squared going to be equal to? X squared plus y squared. So what's x squared? 1. What's y squared? 3. So r squared is 4. So r, I mean, I have a choice here. I could either do plus or minus 2, but if it's up to us, I always choose the positive one. Okay, I don't want to like trick people. So I'm going to just take r equal to 2. Okay, that's what r is. And what about tangent of theta? So tangent of theta is equal to y over x, which is just, what's that? Negative square root of 3, yes? Over 1. And just to kind of make you think in the right direction, so this is like negative, let me write it this way, negative square root of 3 over 2 over 1/2. Maybe that will help you, because what is tangent? Isn't that just sine over cosine? Yeah? So that means I need an angle where the sine is negative square root of 3 over 2 and the cosine is equal to 1/2. What angle is that? What do you guys think? When is the sine function equal to the square root of 3 over 2 and cosine equal to 1/2? What angle is that? Isn't it 60 degrees? Pi over 3? But here I want the sine to be negative. Yes? Pi over 3 would have given me, right, 60 degrees would have given me a sine value of root 3 over 2 and a cosine value of 1/2. But I want the sine to be negative. Therefore, instead of pi over 3, I should do negative pi over 3, right? So theta is equal to negative pi over 3. Okay? Theta is equal to negative pi over 3. So in other words, r comma theta is just going to be 2 comma negative pi over 3. It's interesting. Yeah? Does that make sense? I think I actually have this thing sketched out in the slide itself, just so that you are aware. Okay? So the point is 2 comma negative pi over 3. Yeah? And by the way, I want to say here, we actually had several choices for theta. We could have used anything coterminal to negative pi over 3. Like for instance, I think someone said 5 pi over 3, didn't they? Yeah? And by the way, we could have also been sneaky, okay? And we could have had a negative value for the radius, yes? Then we would have had to change the angle to the other side of that radial line. It's like negative 2 pi over 3, for instance. And this is like basically everything. We'll kind of revisit this tomorrow, though. Okay? That's it for now.